Hi, welcome to the video tutorial on AutoAI Expert System for automated AI design scaling. This is powered by the knowledge graphs and RAG system. For the purpose of demo, we'll be using Jupyter Notebook throughout, and this code will be hosted in GitHub, and which you can use it and improvise the base code that we have provided. So basically in this notebook we want to demonstrate how an RAG based system can power the two critical components of our AI vision pipeline system. So those two critical components are AppLayout and ScaleLayout. What is AppLayout? AppLayout is basically an logical blueprint for an ensemble AI, where let's say for a vision pipeline you have a decomposition of the whole AI that you wanted is decomposed into smaller units, and that unit, how it is connected, how it is interconnected, will be given as a blueprint, and that will be executed in the scale layout. So execution part is a little bit of scale layout, but here the blueprint, it's a logical blueprint, architectural DNA of an ensemble AI or a higher AI application. It's a mastermind that meticulously deconstructs complex and high AI use cases. So bigger AI use cases are broken down into a smaller interconnected reusable AI blocks. So to know more about AppLayout, you can click on the link here, and you can think AppLayout as a master chef recipe where several recipes come together to form a single dish. Here each unit or a block in the ensemble AI, it can be an intelligent unit or a non-intelligent unit. Intelligent unit, I mean, is an AI model or algorithm, and non-intelligent unit could be it's a policy or a piece of code. So here the ensemble will be in kind of a structure, or kind of a DAG structure, where since it's a DAG structure, various permutation combination we can achieve with the help of units or blocks. So flow here, again, data flow can be of different ways. So one could be in sequential, asynchronous, conditional, cyclic, acyclic. All this sort of data flow is possible with the AppLayout. Our years of experience and expertise on a vision AI pipeline system will be distilled into an automation now, and we are trying to create a miniature of AI twin, who is an expert system in vision AI pipeline systems. So to know more about AppLayout, you can go to this link. So next is ScaleLayout. ScaleLayout is basically an strategic deployment commander, we call it as. So basically what it does is it takes the blueprint created by the AppLayout, and it takes the information about the infra available, and with that it will try to optimize and deploy the blueprint. So basically ScaleLayout is an intelligent deployment strategist or an operational mastermind of an AppLayout's execution. So AppLayout is a static, its runtime is nothing but the taken care by the ScaleLayout. ScaleLayout does the AppLayout's execution. So if AppLayout answers what and how, then ScaleLayout conquers the question with where and how efficiently. So basically it has it requires the information about the hardwares we need to provide in our query whenever a scale layout comes into picture, and all the units that is being marked by the AppLayout will be deployed on a unit hardware, and the scale layout has its own goals and rules set, so it has to take care of its goals, and also it has to follow all the rules that we have given to the scale layout. So with that it will try to efficiently do the deployment planning. So just to summarize, AppLayout, what to process, and how to structure the DAG, the bigger AI into smaller decomposable units, whereas ScaleLayout, where to deploy and how to optimize the deployment. If AppLayout is about logical architecture, then the ScaleLayout is a physical execution of it, and if AppLayout is in functional design, and then about performance reality checks, you need to go through the ScaleLayouts. So scope of the AppLayout and automation. So traditionally how this AppLayout and ScaleLayout is generated is without an AutoAI in between, where expert system is required, expertise is required, who will sit and design the AppLayouts and ScaleLayouts what use case you require, what sort of components. This will be meticulously planned by an AI expert, and then it will be deployed. Even for deployment, they have to take care of all the necessary optimizations into consideration. So then it will go for a deployment, and once the deployment plan and AppLayout plan is ready, it will be given to the AIOS execution unit. So and AIOS will take care of deploying those units that is being planned by an expert. So this is how a traditional system used to work earlier. So now we want to demonstrate how we can bring a revolutionary shift where the knowledge which is there with the expertise knowledge can be put it into a rack kind of a system, where rack system will provide you the app layout and scale layout that your user is querying. So this is what the scope of this demo would be. So app layout, basically app layout is a rack structure which runs some use case in a vision pipeline. So purpose here is to create an directed acyclic graph structure for user queried use case. App layout automatically designs process pipeline based on the requirement with the help of knowledge which is there in the knowledge graph. And the function is automation design processing pipeline based on the user requirement. So here RAG is helping us in getting all the information about building blocks, how to construct a pipeline. All those informations will be delivered to us by RAG. And similar to the scale layout, so it is about deployment planning and hardware optimization. So here plan is to deploy this across a number of servers, and again you have some optimizations and resource distribution, resource constraints. All those things has to be taken into consideration. And again RAG here helps us by giving those rules required, or a history of how to do optimization, what needs to be planned. All those informations RAG will help us in getting that. So what is the constitute of our knowledge base? So basically for app layout, we have provided a lot of files to the app layout knowledge base. It can consist of model cards, details about individual AI models, and it could be a policy card. So policy here is again piece of non-intelligent code. We have several piece of policies written, so those informations will be available in the policy cards. Parameter tuning, so if you have certain restrictions or constraints on a use case, let's say about accuracy, about a speed, so for that what parameters needs to be tuned, so such kind of informations are provided here. Pipeline compositions, how to build bigger pipelines using smaller blocks, so general informations are provided. And about input and output formats, like each model, each policy, they have their own input output format. So about the format specifications has been given to the app layout, and also the use case cards and chaining blueprints. So certain examples of certain use cases are already provided in the app layout, and how they have to chain. It could be a sequential, parallel. So how that needs to be connected is provided in the certain files of knowledge base. So that knowledge base, you can access it within this Jupyter notebook, where the knowledge base is the folder name. So if you go inside here, you will have all those files available. So they will be generally MD files or a JSON files or a text files. And for a scale layout, it's all about hardware optimization. It's about estimation of resource for a given the models, given policies, how to estimate it, how to plan, how to club the multiple inputs coming in to form the optimization, and how to reuse the model, how to estimate the streaming resource usage. All those things, the knowledge base data will be provided in the scale specific knowledge base, which you can access it in scale layout files. To prerequisites, you need to build the Docker present in the source code, and once Docker is built, you need to run the Docker and then run the Jupyter notebook. How to run this Jupyter notebook? Inside this Docker is provided in the top. So Jupyter notebook allow port, you have to run this command. So once Docker is built and Jupyter is run, you are good to go. You can start exploring this Jupyter notebook. So here the process flow. So basically this process flow, you can say like three main process. One is first is to set up a VV8 vector database. So in our example, we'll be using VV8 DB vector DB to store our embeddings and graphs, and information related to the knowledge base will be stored in the VV8 vector database. And then phase one, where in this phase we will churn out the data which are in terms of MD files and JSON files. We will read them all and we'll create a queryable data into the vector database. And in phase two, we will we'll give a query and retrieve the data present in the database to construct the AppLayout and ScaleLayout. So block diagram, so indexing, it's the first phase, so where you have a knowledge base full of ScaleLayout and AppLayout files. So they are given to an embedding model, which is right now in our case, in this example, we'll be using a ChatGPT based model. So these files are broken down into chunks, and those chunks are given to this embedding model, and the returned embeddings will be used to construct a graph, and this graph will mainly have semantic relationships which are when chunks are nearby, they will be, if their chunks are of same file, they will be sequentially connected, and if the chunks of different file, if they are semantic similar, then we will connect those two chunks with similarity edge between them. Graph is constructed, and the graph will be put into the vector database. In the phase two, a user query will come. It could be query related to AppLayout and ScaleLayout, and the query is then sent to the embedding model to create an embedding for it. And then with the help of embedding, we will be querying the vector database, whatever the knowledge that is required to decipher this query will be available in vector database. So that has to be queried, and the retriever will retrieve all the chunks that is needed to answer this. So if it gets a straight chunk, so then we call it as initial nodes, and upon this initial nodes, we will again walk through towards its edges to check any similar chunks are available, so that we call it as a neighbor chunks. So initial nodes and neighbor chunks are collected together, and then that forms a whole big context for a LLM. And but this context we will not send it, because here certain chunks may not be of that useful for the user's query, also might be present. So we use a re-ranking model, which is basically a sentence transformer. User can try with better re-ranker model. In our case, we'll be using sentence transformer here. And once the sentence transformers re-ranker model works on the retrieved context, so it will filter out only some top k, let's say from 20 or 30 chunks from it, and those 20 to 30 chunks will be sent to the LLM. So the LLM that we are using here is Gemini for Flash. You can use any LLM you want, and the LLM will generate the final response for you for the user query. So the LLM only will give you the response for AppLayout and ScaleLayout, and only the context will be providing it via our retriever. So this is the whole block diagram of our demo. So let us set up VV8 first. So there is a VV8 setup folder. It has files required for running the VV8. I'll not be able to run it because from the Jupyter, because the VV8 needs to be run outside of the Docker environment. So you first create the folder, and once folder is created, you just have to run the Docker compose, and the Docker compose will run the VV8 container, and the folder that it is will be used is VV8 data in the VV8 setup folder. So whatever data that we will dump into the VV8 will go and set in this particular VV8_data folder. So anytime if you want to remove or clean your VV8 setup, you can always down the VV8, then clean this folder, and again you can start it. so that the now vweight can be vweight is fresh. So first we'll go to phase 1, which is the indexing key. So since we are using Gemini and OpenAI, so definitely the API keys of Gemini and OpenAI is required. So I request user to provide your keys in this file here, and once you dump your OpenAI and Gemini key, you can replace embedding model or a LLM model of your choice, but in our example we are just giving it with OpenAI and Gemini. So once you put this API key, you can just run this bash file. So it will create one env file, and that env file we need to run it in Python environment now, so that those all are the API key that we have set will be available as an env variable for the rest of the program. So just don't forget this. Anytime you restart this Jupyter notebook, you have to run this command importantly. So let me run this. So it has run now, and next piece of code, which is a Python code, it will just tell you whether the environment variable that is read is properly set or not. Yes, it is set, and it is reading, and it is dumping some in between data to us. So our Python program can now take OpenAI and Gemini key. Now that we have imported the API keys, let's import the main file. So block indexer, which is a main file that you can see it here, the main folder block indexer. So this file we need to import right now, because that has a main code for doing the files, chunking the files, talking to the embedding model, and creating a graph and writing the web PV8. So everything is present in this particular block indexer. And then AIOS instance, which is needed for running the test instance of our code. And let me just run this cell. So once importing is done, now we need to configure the knowledge base directory. That's the knowledge base directory. So that also I'll run now. So once knowledge base directory is configured, other parameters related to the embedding, what is the embedding dimension that we want to store. Right now it is 1024, and also the VV8 related informations are available here. What is the embedding model? Right now we are using OpenAI text embedding model, and then other parameters like related to chunking. So chunking, here we are keeping chunk size as 200, which is basically the chunking will happen across 200 tokens, and each token should have an 50 each chunk should have an 50 token overlap between subsequent chunks. And then the embedding dimension is 1024, and similarity threshold is 0.4. So these parameters are provided for the block indexer. So let me run this cell as well. So one cell is run, it as showing what all information it has set, and then instantiating the next module, the initializing the tester module. So once initialization is over, next is about the executing phase, main one. This is a heavy lifting task. So let us see what's going on here. So when we run this tester.run, what it does is it goes through all the files available in the documentation knowledge base. So it could be a PDFs, markdowns, and JSON etc. And in each file, it will try to get chunks of the chunk size, which is like 200 tokens, and so those and with the overlap of 50 tokens as well. So it will collect as much as chunks as possible from each file, and once all the chunks are collected from all the files of our knowledge base, then it goes for generating the embedding for each chunk using OpenAI's API. OpenAI's hosted API it will use, and once embeddings are received for all the chunks, now those embeddings has to be built as a graph, and it has to be put it into the VV8. So while building the graph, it does few things. So how it's building graph is what I'm going to explain now. So chunk from same file will be connected with a weight of 1.0. So let's say if one file is there, it has 10 chunks. Those chunks will be connected with an a weight of 1.0. And since why it is 1.0, because they are belong to a single file, same file. So that file might have a same content, same semantic similar content. So that's why we are giving a higher weightage to the files within the same chunks within the same file. And chunks across file will be connected with the weight of cosine similarity. So what that means is, let's say if one piece of information, one chunk has some piece of information, that piece of information might be similar to some other file, some other file's chunk. So in such cases, if their piece of information is similar or they are somewhat connected, then they should get a higher weight. So that's why we use a cosine similarity between the embeddings. If cosine similarity between embeddings is high, so then definitely that will be set as a weight for the connection between these two chunks. So these chunks will be stored as a node in vweight and vweight vector db, and along with that its actual original text and chunk id, file name, etc. other details will be put it into the vweight db. And chunk id will start with a 0. So 0 is the first chunk of the file, and here -1 chunk id we have reserved it. I'll explain later. And next, initial graph is constructed with the help of networkx.graph library of Python. So in this initial graph, all the chunks of a single file will be dumped, and sequential edges, which is nothing but chunks of a same file. So sequential edges are created between the chunks if they belong, since they are belong to same file. A sequential edges are created, and if the chunks of semantic similar informations is present, then the similarity edge is created. Here it is sequential edge and here is similarity edge, and that similarity edge will have the weight of a cosine similarity function. And then a property name like from node to node are used in the vweight to construct the graph. So you can go through this file to understand more about how the graph is getting constructed. So once graph is constructed, store everything, graph, node, edges in the vweight for a faster retrieval. And there is an optional like enable summary node. So we have not enabled it right now, because what is this summary node is, for each and every file we take the again LLMs help to construct a summary of it, and that summary will be stored as a separate chunk id, which is the equal to -1. Why we are right now optionally avoiding is, since the LLM at the end, we don't want to burden with lot of context. So to avoid lot of context given to the LLM, so we are just trying to avoid this summary node. Once if in case we are enabling summary node, chunk id with most of the selections will be chunk id with -1 only, because it has a lot of data as well, and also it will map with many users queries. So definitely too much of context will be trying to give to LLM to in response to users query. So right now we are just avoiding it. So it is commented in the blocker indexer.py. So let us run this now. So this will take some time because it has to do a lot of heavy lifting job. So let me run it. So it started picking one by one file, and from that file it is trying to create individual chunks, and there will be 50 tokens overlap between the chunks. So it is going through the ScaleLayout files now, and now slowly ScaleLayout files are done. So it is going through some other files, model cards, parameter recommendation. So it goes through all the files. This will take some 5 to 8 minutes maybe. Once sequential edges are pushed to the vv8, now it is time for similarity graph edges. So it constructs a big matrix. Let's say if there are 1000 chunks, so it will create 1000 cross 1000 matrix, and it will try to calculate the similarity score for cosine similarity distance between each 1000 cross 1000 matrix. And once similarity score is created, and then if the similarity score is beyond some threshold, right now 0.4 is a threshold that we have set, then so those chunks are linked via a semantic similarity edge. So now the similarity edge construction is going on. Now this finishes the similarity edge construction. So it is at the end, it will output how many it has indexed nearly 409 passages here is chunks with 50 token overlap, and 228 sequential edges are created, and nearly 14,300 similarity edges are created. So this is the final result. So this completes the phase 1 of it. Let us start now the phase 2. Phase 2 is mainly v-querying to the constructed graph. So AppLayout specific questions we can query, and as well as the scale layout specific deployment related queries we can do now. So let me just show what we are doing right now. Here is a block retriever.py. So this is the block retriever.py. This is the main code which does the retrieving and talking to the LLM by collecting the context and all the tasks whatever we have explained in the block diagram too will be done by this block index retriever.py. So it answers the complete technical questions, provide deployment recommendations, generate optimized configurations, suggest alternative approaches if in case you are expecting it to, and then the main task, like say whenever user queries something related to AppLayout and ScaleLayout, so there is an embedding model again from the chat GPT. So the embedding model will take the query into it will construct an embedding using the chat GPT model. So this query embedding will be used to retrieve the top care relevant chunks from the knowledge base. So we call it as the sequential nodes. Sequential nodes are collected because they are directly mapping with the embedding, and once sequential nodes are connected, we also try to collect the semantic similar nodes, so using the edge limit. For every sequential node we'll try to query other chunks with the edge limit, and let's say edge limit is 10, so for every sequential node we'll collect 10 more sub chunks, so which are connected to the this particular chunk, and we'll retrieve all those chunks, and then we give it to a re-ranker. And re-ranker here again it's from the sentence transformers cross model. So the re-ranker will try to remove a certain piece of chunks which is not required by the current query, and let's say re-rank top k is 30, so it will at the end from whatever it has collected, so it will keep only the 30 items to LLM, and then LLM generates the response. So we have interactive rack chat here, so which will run in this notebook itself, and also we have for the purpose of better output display, so we have a Streamlit based chat interface also. So first I'll show you with the interactive rack chat interface here. So this is the code which we need to run now. So this will basically set up the rack chat interface. So as you can see here, from block retriever.py it is importing this particular class. This particular class has everything in it, and this is our AIOS instance code which has a test context and block tester code. So let me run now. Yeah, the first cell has displayed what all models are available as a general information. So now it is a chat interface, notebook related chat interface I am going to initialize. And once the chat interface is initialized, I need to run those chat interface in a loop so that it can keep on ask the questions, and I can type the questions, I can give the questions, and it will be in a loop until unless you terminate with either quit, exit, or q command. So right now it's asking for a question. So for the purpose of speeding up my demo, so I will take already stored questions. So I have pasted the questions that I have for an app layout. So what this does, so let's see one by one. So now as soon as we give the questions to it, so the retriever will collect the query, and then it will try to, with the help of embedding, it will try to retrieve all the passages or all the chunks which is near to the query embedding. So here you are seeing a detailed list of all the queries, the chunks it has retrieved. Here is the source name and its source it has given us the result. Here you have score of each embedding, how they are similar. So chunk ID 0, 0, 0, 2, 3, all are the chunk IDs. 0 stands for initial, the first chunk of the file, and type here it's nothing but initial or it's in sequential. So once all the chunks are collected, then comes our retriever. So retriever the cross re-ranker model. So it will try to collect only top 30 from it. So once top 30 is collected, those 30 is displayed here, and those 30 will be sent to the LLM to respond with the query. So right now LLM has given the response, it has given the pipeline breakdown. So I'll not go through here because the similar exercise I'll be doing with the Streamlit as well. So this example is just to show what files it has selected, what files it has finalizing it for LLM is what I wanted to show in this particular video. So if you want to run this interactive tool in the terminal, so you can run like this init test retriever interactive file is provided in the code base here. So if you don't want terminal, now next option is a Streamlit web chat interface. So first you need to generate the Streamlit app code. So you just run this cell. I have already run it. It will create one file to you, and that file is Streamlit track chat.py. So this file will be the created file will be used by the subsequent cells. So you just have to run this cell. I just have to quit the previous chat interface. Yeah, the chat interface is quit now, and let me run the Streamlit based application. Yes, it has pulled all the requirements, and then it has set up the Streamlit. So here it is, the 8051. I've already opened it. Let me just refresh it. So it is setting up the rack chat interface. So to stop the chat interface, you can just call stop streamlit.py, stop Streamlit function. If you execute this, the Streamlit will get stopped. But right now, let it run. So yeah, rack chat interface is ready right now, and let me post the same questions that I asked in the chat interface. So basically I'm asking build a pipeline for a crowd estimation and parking violation. Here I'm providing auto rickshaw information because there are multiple models, and I want my my LLM to choose me a particular model which has auto rickshaw class in it. Use cases separately and call it as AppLayout, and then get its model and their requirement, their usage data throughout for best throughputs for best accuracy. I need just the pipeline details in models in it, and model parameters and use case parameters. No other extra explanations are needed. So why this I mentioned is, since we have given a bigger context for LLM to give the result, so it should not give necessary information. So what is needed, only it has to provide is what my requirement is. So for the crowd estimation, app layout is generated, and app layout input and object detection will be there, and there will be a policy filter, and a crowd gathering use case code will be there, and it has given the tag for each and every block. We can call it as a block name or anything. So object detection, it is in general object detection 360 cross 360 640, and its model parameters are provided here. So it can it will take the input of with resolution for the model resolution is 416, whereas it takes the input which is of 640 cross 360, and then batch size is 8. Certain confidence thresholds and NMSIO thresholds are provided here, and then comes the policy filter. It requires certain parameters: allowed class, confidence score, and zone. Allowed class is mainly to, from this object detection, only allow the person class is what we are trying to say to this policy. And since it's an object detection model, so it will omit object with a different confidences. So I'm trying to filter out only objects which are more than 0.5. And this zone crowd. So basically zones is nothing but a virtual area drawn on the viewpoint of the camera. So whichever objects we are tagging that zone as a zone crowd, and whichever people objects, basically person who are inside the zone only, will be filtered from this particular block. Then the crowd gathering use case logic will be run here, which requires certain parameters like count threshold. So right now here it's 20, which is defaultly set in this particular file. So this 20 is nothing but number of people. If they are exceeding it, then alert will be thrown. And violation frame counts, like how frequently, how many frames, if 20, more than 20 people are present, then it is a violation scenario. So that's what this violation frame count is. And alert interval between each alert should be of 600 seconds, which is 10 minutes, and severity is medium severity. So this is the app layout of a crowd estimation. And then parking violations app layout. So again, similarly, since it is auto rickshaw is required, so it has chosen certain particular vehicle detection 360, 640. So it has a vehicle detection model. Then there is a policy one, there is a tracking, vehicle tracking is required, dwell time policy is required, and a parking violation use case is required. So here different parameters are provided for a vehicle detection, which is similar to object detection. And also for vehicle policy filter, it has given this kind of classes, and it requires a zone and a zone parking. And there is a tracker also, it has certain parameters. The parameters are provided here. And for a dwell time, so some parameters are provided, loitering threshold second, 3 seconds. So minimum 3-second objects will be sent out of this policy. And if a reset period, so if an object is not getting tracked, or object has ID has lost the ID, it has regained some new ID. If object is not available more than 10 seconds, so you just remove those IDs, is what the dwell time policy is doing here. And parking violation, so it's a use case logic, so where violation threshold of 120 seconds is set. So if vehicles are staying there, dwelling there for more than 120 seconds, then it will be alerted. Alert interval of 600 seconds, which is 10 minutes, and severity of medium. So this is the whole app layout given for the app layout query that we have requested. And now that app layout question has been done, we'll check about the scale layout. So here is the question. App layout you have decided for crowd estimation parking violation with the models pipeline, then FPS requirement. Ignore the FPS from app layout, because app layout also will try to give certain FPS, which I don't want. I want an optimized deployment plan to be estimated. Following is the data I have for the task. So here the number of servers, there are 2 servers with 3 GPUs each with NVIDIA test 34, 16 GB vCPUs per and vCPUs per server is 64 and RAM per server is 128 GB. Camera streams is 20 streams that I'm trying right now with full HD HDR 15 FPS. And I need to provide the camera matrix for this 20 cameras that I have given. So here camera matrix is basically I'm needed for crowd estimation and parking violation. Here camera 1 to 6 are having the crowd estimation, and camera 7, 8 and 9 and 10 has both the use cases where crowd estimation and parking violation is available. And 11 to 16 has parking violation alone, and 17, and from 18 to 20 again crowd estimation parking is available. So from app layout understanding, come up with a plan where to deploy the what use cases, group the camera accordingly, make sure you follow the rules set by ScaleLayout. So this is the question that I'm posting to the retriever plus LLM. Now retriever try to understand this embed and get the embeddings for this particular message, and then try to get fetch the passages from the V8. Only problematic can be like right now the retriever doesn't know about the history at all. So what a blueprint, what app layout has been created, those informations are not available. Only with the query only it is trying to get the required passages, and then it will try to give that to LLM. So now responses come. So yeah, right now the context doesn't provide the CPU RAM and GPU RAM for track light pod, which is a part of a parking violation use case. Yes, that's true. Possibly the retriever couldn't get the details related to those pods. Context also does not provide metrics for generic policy and use case pods as well. So yes, that is possible. That's what the limitation of the current retriever is. It doesn't know about the history. It just takes the current message into consideration, current query into consideration. Therefore, all resource calculation of set 2, set 3 are incomplete, and final node resource usage will be slightly higher than the estimated here. So right now, cameras with crowd estimation only. So it is trying to come up with 0.25 as the FPS, because in the scale layout we have mentioned for crowd use case point, it will start from 0.25 use to 5 FPS. So in that, its minimum is 0.25. For parking violation, it is 0.5 FPS. Again, for parking violation, this was the range of FPS it can take. So in that minimum, it has chosen. And use case with both crowd estimation and parking violation, it is trying to finalize 0.5. The reason being is, in this it will try to identify overlapping FPS, and in that it will take the minimum, which is 0.5 FPS. So the FPS has been identified, and set also is decided. So one is crowd estimation set, parking violation set, and a hybrid set where crowd and parking both will run. And it will try to estimate the event received per tick. So what is this basically is, whatever the FPS you have, and multiply the number of cameras and a 60 seconds. So tick here is, one tick here is basically 60 seconds, because the data that we have is like this for every 60 seconds, and we'll estimate what is the event received. And for that, we have the CPU and GPU, CPU RAM and CPU vCPU is required. So that's why we have to get the event received per tick for the current model. So current sets. So for crowd one, for a first set which is having only the crowd, you have 6 cameras, 0.25 FPS into 60, which is like 90 is the event received per tick. And its vCPUs is estimated, interpolated from general object detection. It has interpolated to around 52 M, and 3.42 GB RAM is required. Similarly, for parking violation, event received per tick is for 7 cameras with 0.5 FPS into 60 is 210. And for 210, it has done some extrapolation from this vehicle detection model, which is like nearly to 52 milli vCPUs and 3.24 GPU RAM. So resource for tracker light are missing. Yes, that's true. And also for use case as well as policy as well. And for hybrid, it will again club for object detection. It has to get for not 90, it has to get it for 210. And vehicle detection, it has got 52. So totally it is 103 M for 210 event received per tick. And RAM is also general object detection requires this much, and vehicle detection requires this much. So total it is 6.49 GB of a RAM, a CPU RAM. So tracker lights are missing. So now let's calculate the GPU resources, where GStreamer decoding per stream. So we have given this information in our history, the knowledge base. H265 full HD 15 FPS requires somewhere around 169 MB of RAM per stream. So for crowd set, which is having 6 cameras, it will try to multiply the 6 streams into 169, which is around 1 GB. And total RAM required is nearly 3.3 GB, because 2.25 GB of RAM is required by the general object detection, a GPU RAM, and 1 more GB is required for the streamer. So that's why the total sum is 3.3 GB. And for parking, 7 cameras, vehicle detection requires 1.9 GB, and 7 streams requires 1.8 GB, 1.18 GB. So total is 3.7. And for hybrid, so it has 2 models. One is general object detection, it has a vehicle detection, and also the 7 streams. So it is 1.183. So total is around 5.5 GB. And now it is doing assignment. So GPU 0, hybrid 7 cameras has been assigned, set 3, and GPU 1, set 1 crowd 6 cameras has been assigned, and it has not assigned anything on GPU 2 of the node 1, and GPU 2 of in the node 2, GPU 0 has been assigned with set 2, where parking violation alone is running. So these are the estimated vCPUs and RAMs for the system, and so the plan distributes the workload across both available servers. So that's what we have given as a instruction. So first try to use all the servers given, then try going deep in one server. So that's what it is maintaining. So it is trying to handle the fault tolerance here. So even if one server goes, some more license from some other server has to run. That's what the strategy is. So node 1 handles 13 cameras stream across 2 GPUs, and node 2 handles 7 cameras across a single GPU. So for the tracker light and policy and use case, it has not estimated. So it could be little more than what it is showing here. The only reason being is our retriever has failed in getting it, so getting these details. So that's why we need to make our retriever a little intelligent. As LLM has a history of messages, the retriever doesn't have a history of messages in when it generates embedding or when it queries the VWeight. It doesn't takes anything about the history of queries, user queries. So that's why it might be missing those details. So this completes the scale layout portion of the our chat interface. So where we have used RAG based application to do the automation of AI AppLayout and ScaleLayout. So you can improve a lot of things can be improved, or different approach of a RAG can be utilized here to get the AppLayout and ScaleLayout. So this is just maybe a starting point. I request user to go ahead and further improve upon this base code to get better results.